In this problem, we're going to calculate the adiabatic temperature for a reversible reaction. So we're looking at a simple A goes to B liquid phase reaction. And the question is, what's the adiabatic temperature and what's the conversion when we feed pure A to reactor at 300 Kelvin? I'm going to simplify the problem by making the heat capacities constant and equal. Because they're equal, this means the heat reaction doesn't change with temperature. We're given the equilibrium constant at 298 Kelvin, which we could have calculated for some tables if we knew the components of the reaction. And in addition, assuming the heat capacities are independent of temperature, we're going to assume ideal liquid solution. And so essentially what we're looking at is a balance between how much reaction takes place and how the equilibrium constant changes. Exothermic reaction, as we raise the temperature, the equilibrium constant decreases. And so that means the rate's going to slow as the temperature goes up. The reverse reaction becomes more important. And we're eventually going to approach a point of equilibrium. And this is going to be independent of the type of reactor, whether it's a plug flow reactor, continuous stirred tank reactor, batch reactor. If we're running it adiabatically, we're going to get the same result. So we need to write down two equations. First, let's look at the relation between temperature and equilibrium conversion. So we're looking at the Van 't Hoff equation, which relates equilibrium constant at temperature 2 to equilibrium constant at temperature 1. And that's related to the heat of reaction, the gas constant, and then 1 over temperature 1 minus 1 over temperature 2, where of course the temperatures have to be absolute temperatures. Well, we know the equilibrium constant at 1 temperature, that's 10 to the 5th, and we know the heat of reaction, 20,000 calories per mole. We're going to use a gas constant that has the correct units, and then we know 10 to the 5th equilibrium constant is at 298, and then we want this in general for other temperatures. So the equilibrium constant K2, and we use that equation along with an energy balance. Before we do that, let's look at how we're going to relate the equilibrium constant to concentration. So A goes to B reaction, the equilibrium constant, ideal solution, because of the stoichiometry, it simplifies quite a bit. This is the equilibrium concentration of B, the equilibrium concentration of A, and we can write the equilibrium concentration in terms of the conversion of equilibrium, in this case just to make it easy to simplify the equation. So the equilibrium constant equal to Ca0 times conversion equilibrium, so that the conversion equilibrium is related to the equilibrium constant. And of course, the equilibrium constant is this term here, which is a function of temperature. We're now going to combine that with the energy balance. We're going to do an energy balance adiabatic reactor. So essentially, there's just two terms. All the energy from the reaction goes to heat up the feed. So if my flow rate coming in, FA0 is a molar flow rate, moles per time, molar heat capacity. The exit temperature, this is the exit temperature, this is the feed temperature. Exit temperature is higher than the feed temperature, and how much is higher is determined by how much heat's released by the reaction. So this is heat reaction per mole, so we need to know the moles of A that have reacted. So this corresponds to moles of A reacted per time. And so that means this equation we can also apply at equilibrium. Equilibrium temperature corresponds to equilibrium conversion. So X at equilibrium comes the heat capacity of A, equilibrium temperature minus the feed temperature, minus the heat of reaction. This is 50 calories per mole. Feed temperature is 300. This is equilibrium temperature. And the heat of reaction is minus 20,000 calories per mole. And I left out the heat capacity, calories per mole per Kelvin. So the units are going to cancel temperatures in Kelvin. We get equilibrium conversion is equal to equilibrium temperature minus 300 over 400. So this equation combined with this equation where K equilibrium is this value is what I want to solve now simultaneously. So I've drawn here just a freehand plot. The energy balance is a straight line shown here, relation between equilibrium conversion as temperature, and the equilibrium conversion as a function of temperature starts out at a value essentially 1 because the equilibrium constant is 10 to the 5th at low temperature. As we raise the temperature, equilibrium conversion decreases. So for an adiabatic reactor, this is the point where we're now have the reverse reaction equal to forward reaction. We're satisfying all these equations. If we solve these simultaneously, we could certainly do it graphically, or we could put it into solver. We find that this point corresponds to an equilibrium temperature of 460 Kelvin and an equilibrium conversion of 40%.